Okay, now that we know how to calculate the concentrations at equilibrium and Kc at equilibrium, which is equilibrium, sorry, we can now apply different applications of the equilibrium constant with our now known knowledge. So we can predict whether the direction of the reaction is going to go forward or reverse. So let's look at an example of this. So if I give you N2 plus 3H2 and we make ammonia, and the Kc of this reaction is 0.105, let's say that I give you concentrations of 2 molar of H2, 1 molar of N2, and 2 molar of NH3. Can we predict how the reaction will move forward? So let's look at this. So ultimately, we know that we're doing the concentration of our products over our reactants when we do a Kc. But in this point, we don't know if we're at equilibrium or not. So what we can do is we can say, okay, well, I have 2 molar of NH3, and that's going to be squared because of its coefficient. And I'm going to divide that by the 2 molar, that's to the third for my H2, and my 1 molar to the first for my N2. And if I do this math, I come to get 0.500. Okay, however, Kc is 0.105. So this number right here is telling me that I'm not at equilibrium. Because if I was at equilibrium, the number should be 0.105. So since the starting value is higher than our Kc, how can we shift the reaction to make it smaller down to 0.105? Okay, well, there's a couple of different things that you can do. You can, to make it smaller, you can decrease the numerator, which means our products, or you can increase the denominator, meaning our reactants. Ultimately, we're just manipulating the fraction to get to the value that we want, okay? And we don't need to manipulate it, we just need to be able to talk about how we're going to shift the reaction. So in this case, we can shift the reaction to the reactants to make our number smaller because we want to make more reactants, okay? The value that we just calculated is not Kc, we already proved that, but it's referred to as the reaction quotient, which is Q. And there's 3 different possibilities that we can have for Q. Okay? So for example, if the system is already at equilibrium, this one's an easy one. Our Q will be equal to Kc. That means we're at equilibrium. That means we don't have to shift the reaction. Okay? However, if the products are greater than the reactants, meaning the reaction will move right to left. Okay, so in this case, Q will be greater than K. And that makes sense because if Q is larger, that means we have more products. Okay, so since we have more products, we have to be able to move the reaction back to the reactant side in order to get our number down lower. Where if the products are smaller than the reactants, the reaction will move left to right because we have to make more products. And in this case, Q is going to be less than K. So you're responsible for knowing that if Q is greater than K, we have to make more reactants, where if Q is less than K, we have to make more products. And that's basically the gist of this section.